So I would like to show you a simulation of double slit scenarios in various circumstances, and not only double slit, just a simulation of certain things. So let's start with a classical wave. I shoot light through double slit. Let's see what's going on. Okay, so this is electric field, and you can see as electric field passes through slits, it diffracts. So I can pause, it diffracts. Sorry for the low resolution. This simulation works best on low resolution. It diffracts, and you can see zones of constructive interference, the three zones of constructive interference. In FIS2, we call it nodal, antinodal lines. And then you have nodal lines where you have a destructive interference. You place a screen, the nodal lines lead to dark spots and the antinodal lines lead to bright spots. So that's just what we've been discussing in discussion sessions. Double slit interference, classical picture. I'm plotting the electric field. I can also plot the time average intensity. Intensity is the square of the magnitude of the electric field. That's also periodic in time, but if you average over one cycle, you get a time-independent quantity. I can also, let me move the slits a little bit. Well, it's okay. I can also measure, let's say I have a hypersensitive measurement on the screen, and I can actually measure hits of photons, and you can see very rapid accumulation, and the density of accumulation matches the intensity pattern, right? So let me show you again. I'm going to make it a little bit less bright right here. So this is, yeah, okay. So you can see photons ping, 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 ping. I can repeat the same thing by shooting individual photon at a time, individual photons, one photon at a time. So I'm going to go here. I'm going to clear, reset. So I'm going to place the double slit. I'm going to shoot one photon. So here's the electric field of one photon. So it's going to be like a wave packet, like a single wave packet. Imagine a pulse. It's a pulse. So here we go. Boom. It's on repeat. Let me turn off the repeat. So here's a pulse. And what you're seeing, that's the electric field of a photon. When I actually perform the measurement of the position of where the photon is, it will be localized. So when I ask of the photon, where are you? Photon says, I'm here. And it manifests itself as a particle, as a dot. So you can see right here. Boom, right there. Photon is right there. Before I make the measurement, the position of the photon is not defined. And all there is just the field, the electric field. Again, I can plot time average intensity instead of the field. It would look like this. And this being the wave, it diffracts, right? Like any other wave. CCS, when it passes the slits, it diffracts. It forms zones of constructive and destructive interference. The zones of constructive interference, when they hit the screen, that's where the intensity is largest. And in the wave-particle duality, we reinterpret the meaning of the intensity of the electric field as a quantity that gives us the probability of where the photon is most likely to be found. So where the intensity is larger, that's where the photon is more likely to be found. I can remove the slits. I can just shoot a single photon. So this is, again, this glob, this is not a photon. This is the wave aspect of the photon. For photons, the wave aspect is the electric field. The square of the magnitude of the electric field is intensity. In the wave-particle duality, the intensity is what gives us the probability of where the photon is going to be found when we try to make the position measurement. So you can see this intensity wave is moving It's largest here. Color represents the value. It's largest here. It's weaker here. It's very weak here. And this says that when this wave hits the screen, most likely we're going to find the photon here. We might still find it here or here. So let me repeat this. Oh, okay. And I'm going to repeat this again. Move faster. Boom, right there. Every once in a while, we'll find photon somewhere on the fringe. So let me do the auto repeat. Every once in a while, it will be found somewhere on the fringe right here. But most of them will be found where the, right there. You see, we found the photon here, where the probability is actually quite small. Right here, let me see if I can catch. Right here, where the probability is small, nevertheless, the photon materialized. I had a question this morning. A student asked me, if things are random, how come you have a, why is it that, how come there are spots where it's more likely to find a photon? Random doesn't mean that the probability is uniform. If you shoot darts at a target, the darts land randomly, but the distribution of landing locations is not uniform. They're still more likely to hit the center than the edges. The extreme case of that is when the probability distribution is very, very narrow, it reduces to deterministic situation. So there's a whole set of intermediate cases where it's not deterministic. It's random, but the randomness is distributed in accordance to some probability distribution. We will spend probably entire Tuesday doing a review of probabilities. So, okay, so here's the probability distribution, and that's where the photon is going to be found. Of course, the probability distribution is a wave. I can, for example, put an obstacle. I can put a, instead of slits, I can put an obstacle. And if I put an obstacle, right? So if I put an obstacle, what happens when the wave hits the obstacle? It will flow around the obstacle and it will change. It will diffract. Waves diffract. Waves diffract. So here you go. A wave diffracts around the obstacle. So you can put obstacles, you can put slits, you can put anti-slits. You can do something like that, for example. If I shoot a wave will diffract. And so now you see when a wave diffracts, let me pause right here, the wave becomes a complicated, it acquires a complicated pattern. And so the intensity field is complicated. And so the probability field is complicated. So you can see there are zones of destructive interference. How do we interpret that in the probability language? Well, that's where the particle is less likely to be found. There are zones of constructive interference. How do we interpret that in the probability language? That's where the particle is more likely to be found. So if I repeat this many times, you will see that there will be, if I collect statistics, in fact, let me do this. I'm going to pause. I'm going to collect statistics, and you will see bands of where the photons will be. I'm going to pause. So we don't have to waste time watching how statistics accumulate. Okay, so I accumulated some statistics. I had to move this obstacle with the hole a little bit lower so the pattern would become clearer. So you can see when the wave diffracts, there are very strong zones of constructive interference here. In the wave-particle duality, we interpret that as these are the zones where the probability to find the particle is largest. And this zone of strong destructive interference is interpreted as the zone where the particle is less likely to be found. By the way, if I was finding the particle on the floor, not on the wall, but on the floor, for example, at this instant, if I tried to make the measurement, I'm most likely to catch the particle here. I'm quite likely to catch it here. I'm very unlikely to catch it here, and almost completely unlikely to catch it here. So the quantum picture is that the particle has both wave and particle properties, and the wave property is that what is used to predict probability of where you would find the particle if you were to try to make the position measurement. And there are other measurements that you can make, and the wave contains information about that as well. So what if I switch to electrons? So let me reset. Let me make everything clear. I'm going to pause. I'm going to disable slits, and I'm going to switch to electrons. So the program has to adjust a little bit. And again, without slits, without anything, I'm going to shoot one electron at a time. So here come the electron. Oh, I want to disable auto repeat, and I want to disable rapid. So here comes the wave. What is that wave? What's the meaning of that wave? It's not electric field anymore. No, 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 no. We're gonna move off from photons. Photons were a stepping stone. Now we're gonna deal with things that we traditionally think of as particles, for example, electrons. What's the meaning of this wave? What is this a wave of? Well, this wave is a new kind of wave. It's called a wave function, the one that I represent by Greek letter psi. What's that wave function good for? Probability. The square of the magnitude of the wave function is what tells us the probability. So if I repeat this, if I put this on auto repeat and I shoot these things, you can see where that wave function hits the screen. That's where we're more likely to find the particle. And notice the wave function of the electron, it spreads differently than the electric field of a photon. It's not electric field, it's a different type of wave. It's called a wave function. It doesn't have a physical meaning. The only meaning of this wave function is that it gives us the probability of where the electron will be found if we make the measurement. So before we make the measurement of the position of the electron is not defined. When we do make the measurement, for example, by placing the screen, we can get an electron at various locations. It's unpredictable where the electron is going to be, except that we can predict the probability distribution. So let me try to catch it right here, right? The wave is about to hit, and this wave, the wave function, I'm plotting the magnitude of the wave function, it tells us that it's more likely that electron will be found here than here. Okay. Now this is a wave function, it's complex. We will discuss complex numbers and complex functions next week. Some of you know a little bit about complex numbers. They have a real part. So this function has a real part and it has an imaginary part. And what I'm plotting here is I'm plotting the magnitude, the square root of the real squared plus imaginary squared. So the use of this wave function is to predict probability distribution of the outcome of position measurements when you actually do make the measurement of position. A wave function is a wave, and as any wave, it diffracts. So I can place double slits. I can make the slit width smaller. And when this thing passes through the slits, it will diffract like any other wave. You can see it's a wave. It's a wave. Wave diffracts. But what is this a wave of? Well, it's a wave that gives us the probability information of where we're likely to find the particle. So you can see the way it diffracts, it develops two zones of constructive interference for this particular slit arrangement. And so you can tell me where, make a prediction, where am I most likely to catch an electron? I'm about to catch an electron. Well, it's probably going to be here or in the center. But it's a little bit less likely to be here or here, and very unlikely to be here or here. Let's see how it works out. Yeah, so I need to make this a little bit brighter. And let me move the slits a little bit closer. The wave was spreading out too much. So I'm going to shoot another electron. Here comes this sorry, I'm going to show, here comes the wave function of that electron. The wave function is about to hit the slits and it will diffract like any other wave. And I'm more likely to find an electron here or here or here than here or than here. Let's see. Oh, right there. And let me put this on auto repeat. Sometimes I'm not sure why this works. So you see electrons accumulate right around where the magnitude of the wave function is largest, right? So you can see the zones of constructive interference right here. And if I let it accumulate, I'm gonna get basically 3 globs in the center and 2 on the edges. So again, let me summarize this yet once again. The quantum picture of predicting particles' future is very different from classical picture. In classical picture, we think of trajectories. Particles follow trajectories. Baseballs follow trajectories. Cars follow trajectories. Planets follow trajectories. In quantum picture, we don't talk about trajectories. We have particles possess both particle and wave properties. The wave property of a particle is called a wave function. Being a wave, it diffracts like any other wave. And the usefulness of that wave, the usefulness of the wave function is that it gives us the probability of where we're more likely to find the particle when we actually do make the measurement of the particle. The position of the particle is not defined until you make the measurement. When you do make the measurement, it will not appear in deterministic locations. The location will be random, but that randomness will be distributed in according to a probability distribution that you get from the wave function. The wave function is a tool for making, for predicting the distribution of where you would find the particle when you do make the measurement. Okay, that's the quantum picture, and I will repeat, and we will use it. We will develop it. We will start working with wave functions. So first, I have to teach you about complex numbers, about probabilities, and about waves. Okay, all right. So that's the simulation part. I will see you in the next part.